Hey, good day, everyone. This is Professor Burns, and I am glad to welcome you guys back to the lecture for this course. This is lecture 6A, and we're going to be talking about a few things today, but they all surround basically cache and how we would use that to map different things or to enhance what we're doing in terms of accessing memory. So we'll go over the memory hierarchy. We'll talk about caches, and then as a part of that, what associativity is, some of the right policies that are used, and then we'll also talk about replacement policies. So now, if we go back and we kind of reflect on where we started with the class, the intention of this class is to learn how we can program more efficiently in order to effectively or program more effectively in order to be efficient in terms of what the computer's doing, right? So we talked about three main categories that are going to greatly impact your computer, right? Your power, that means how much power am I using? How much does the system have? Am I drawing a lot of power because I'm using a bunch of things for the CPU? Am I making the battery die very quickly because I'm trying to do a lot of processes, or just because I'm requiring a lot of work from it? We talked about processing as well. How can we enhance our CPU and GPU ability? And we talked about memory. Now, what you notice is that memory is part of processing, and then memory itself is also a category because, as you guys will know, your memory is going to impact the ability of the computer to process things, right? A lot we talked about some of the components of a computer are like RAM or random access memory. The more RAM you have in your computer, typically the quicker you're able to process information and do this multi-level applications because now you have more memory to access, right? And then there's also where you're storing information. You want to have a good amount of memory there as well, right? So now that we have that, we have this basis. How do we get to a point? We've talked about extensively how we can, how we and see how we access the memory, what the different components are, and ways that we can optimize that by using, for example, if we use a union data structure as opposed to a struct data structure, the union is going to take up a little bit less memory because it puts it all in one spot. Well, are there other ways that we can be more efficient in memory? And the answer is yes. And this deals with both programming and also the hardware itself. So let's look a little bit at this computer hierarchy, right? We have our processor, right, which is our CPU. Some may call it the arithmetic logic unit. And then we also have the memory. And typically what you'll see is you're going to send data back and forth between these places in order to determine, what do I want to pull? What information do I want to access from um, this particular component? So when I think about this, when I'm accessing data here, I'm going back and forth. Let's say, hey, the processor says X is 5. I have to now go and access this from my memory, which X has all of these slots where I'm trying to access it, and X might be somewhere, I don't know, it might be somewhere, let's say it is right here, right? It could potentially take me a little while to get to that, right? To get the access to that information. And what if I say X is equal to 5, but now I have it in a for loop, right? I want to write something that says that puts it in a for loop and says for I basically incrementing by 1 to 5, I want to add and keep on changing where X is equal to, instead of it being this, what if I said I want to make X equal to I um, plus 5? All right. Then that means that each time I want to access this, one, I have now this, I have this this component here, I, and let's say we have I is here, and then I have this component X. X is accessed 5 times. We keep on going back and forth to access that and to update the value to whatever we want it to be, right? And it could take a little bit of time because it's kind of from the processor to the memory, and I'm going through all of this the sub level stuff. But what if I wanted to access it a little bit quicker? Is there a way to do that? And the answer is yes. Yes, there is a way to do that. And the way that we do that is through a cache. All right, so you may be asking, okay, what the heck is a cache, right? Cache is this place between your memory and your processor that allows you to access those things that you're commonly using. Like we just talked about 5, that when we have that X is equal to I plus, some number, plus 5, what we're doing is each time we keep on accessing 5, right? So what if I could access that a lot quicker instead of me going all the way into memory to update and change that? The cache allows me to bring it closer to the processor and access it more quickly. Similar to, I have these, when I'm home, I have all of our shoes. We take our shoes off of the house, so they're on this rack. And what I do is I have, a particular pair of sneakers or shoes that I like to wear. I always put them at the top, and then the shoes that I wear less often are at the bottom. So when I'm ready to leave in the morning, all I do is grab the pair of shoes that are at the top. And if I find out that, hey, I don't want to wear those shoes today, I want to wear a different pair, what I do then is now I go to the bottom or the middle of the rack. But I don't want to always have to reach down to the bottom for something that I commonly use. It's the same thing with the cache, right? If you don't want to always go down into memory to get it, right? Because each time you access that, it's going to take time. It's going to increase your processing time. You have to sort through a bunch of memory addresses. The cache is a smaller subset of memory, which means it's going to have less locations. And that means I can access the data more quickly. I can then grab that pair of shoes in my case, or I can grab the data from the cache from this subset of memory and not have to jar it from the memory, which will then increase my processing speed. So now if I want to say X is equal to 1, X is equal to 2, X is equal to 3, I can just grab this right here. Boom, 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 boom. It takes a lot less time than me grabbing it all the way from memory. So that is the benefit of having this cache, right? I'm not overwhelming the processor by continuously trying to access the main memory, but I can do it from this subset. So let's talk about a little bit about the cache and how it looks. Now we talked about this is memory intensive. So we are looking at, okay, how can I actually view this data? And then there's going to be certain policies that we use in order to organize it. So, as I said before, because it's closer to the processor, because it has a smaller size, right? You can have a memory that has, thousands and thousands of bytes, right? But your cache is going to be substantially smaller, which means I search less because now I can just access that quickly through a smaller database. So it allows you to access the information or the data a little bit more rapidly. It also speeds up your execution time, right? So I talked about that. If I can pull the shoes quickly from my rack, I can get out the house a lot quicker, right? Whereas opposed to if I have to bend down to that bottom one, it's going to take me longer to get that data. It's the same. It's a similar thing with the processor looking at the memory as opposed to looking at the cache. The longer it takes to get from memory, the longer it's going to take to process and execute a particular program. And finally, it also decreases your performance gap because between being able to access the data quickly and not overwhelming or constantly pulling from the main memory, you're now increasing the performance of your computer overall. And you may be familiar with cache. Sometimes we'll see that on our browsers. What happens is it stores all this information in this cache, right? So anytime you want to go to that site, now you can access it more rapidly, as opposed to if you have an empty cache, or an empty memory, it might take you, several seconds to access a website. But if I store it in the cache and I already know what you're looking for, then it makes it easier and quicker to get to whatever data you're trying to get from that previous website. So now I talked about there are certain policies that are associated with using the cache, right? So we already know that it's between the processor and the memory, right? But how do we go from the cache to the memory, back from the memory to the cache? How do we put data in? How do we get it out? And what does that look like? And also, how can we do it in the most effective manner as possible, right? Because it makes no sense to have this cache if you still basically end up spending the same time searching for the data that you do from the main memory. So before we get into that, let's talk a little bit about these mapping terms. When we refer to data, data is the information that you are trying to access. So it could be data from an array, it could be a command, it's whatever you're trying to get from memory. Your tag is your memory location. So typically when you're looking at a cache, what you'll see is it'll kind of look like this. Well, it'll have these subsets here. And what'll typically happen is this block here is known as the tag. And what that is that tells you what memory address you're in. 0x5, for example, right? This one right here is the data. That's whatever you're accessing. And then there may be, for some, there may be some sort of validation bits and all that you're validation. There may be some validation bits that you're using to determine whether or not this data is actually valid, right? So you're gonna have, you may have this block of data or this item that you want in the cache. And this is kind of what it's going to look like. If you have a line, a cache line, right? You may have something, you're always going to have a tag, right? You're going to have something that tells you where you can find it in memory. You're always going to have data. And then depending on how it's set up, you might have a validation bit or other information to help you delineate and further determine what's in that particular line of the cache. All right, so we have our data, we have our tag, which is the memory location. We have a block. A block is known as a cache storage unit. Now, a block would be kind of the, it's how you're storing the information here in this section here, this block of data. How am I storing it inside here? Line, this line refers to this entire cache row, right? This is one row, and then typically a cache is going to be multiple rows. So you're going to see this multiple times here, right? We're going to start out with one, but then this is repeated and repeated and repeated as many times as you have your particular cache, right? So when we talk about the line, that's one of these. Your line is this whole item, it's one full thing of that. That's your line. A set, right? Remember I talked about one block is one item in here. When we talk about set associative cache, what you'll see is a set is like if I have multiple items, if I have multiple blocks inside here, a set would be two, maybe two of these blocks together. This is block one, and this is block two. A set is going to be a combination of those together, a combination of the blocks. All right, so let's talk about associativity, right? All these terms will help us better understand associativity. Associativity means how are we associating the data with some place in the cache? What is location of the data in the cache, and how are we associating that with the original memory. So there's there's three main types of associativity that we have when dealing with cache. One of them is called a direct mapped version. And what that means is that you map one location to one block in the memory. It's a one-to-one relationship between your memory block and where it is mapped in the cache. The second one is called fully associative. And what that involves with is that means that I can have access to any one of these memories. Any location in my cache, I can have access to it, and then I can map that to a particular location. And then we have a set associative cache. And that means that I have these blocks or these sets that are created, and I can use those to put locations. And now these locations, when I talk about location, I'm talking about the locations or the blocks within the cache. All right, so this will make more sense as we go along. So direct map, right? Remember, direct map means I can map to one location. And what you'll see is here is my cache, right? Here's the tag. That means this is associated with where I'm looking in memory. And notice how it has this tag or this address of, we'll call it 5. And that's the same block that is associated in here with the cache itself. And this is meaning I'm mapping one spot in memory with one spot in my cache. So that's where we get the one-to-one relationship. So let's go ahead and look at an example. Let's say I have this program right here. And very simple. I'm just basically taking a bunch of numbers, running them in a for loop. But it would be, this is just to show kind of how we're looking at things in terms of memory, right? If I have these numbers and I start out with x is equal to 1, where do I store that? And then so on and so forth. So let's see how that looks in direct map. This top one is our cache, and this bottom one is our memory. And notice how each of these is kind of like a one-to-one relationship, right? Between the cache and the memory. So let's start off with int y is equal to 0. If I did that, that's going to map to this same location. This is telling me where this is in memory, and that's where it's going to map. Now let's move on to, if I say x is equal to 1, notice how there's kind of this one-to-one set. It's in this set or this location is the same block in memory. Z is equal to 4, the same thing. It's 1 in memory. It's going to be 1 in your cache. And then finally, we have A is equal to 0. It's going to be 4 in your memory, and it will also be 4 in the cache. Notice how that is mapped in this one-to-one relationship. And what you'll also notice is that it can map it anywhere. It doesn't necessarily need to go in order or sequentially, but all of the addresses are going to be pretty much equivalent to one another in terms of, if I say I'm at address 1 here, it's going to be that block 1 in memory. All right, so that's our first one, right? We go back. This is our direct map, one-to-one relationship. All right, now let's go ahead and move on to a fully associative cache. All right, so if you remember the last one, that last association, there was a couple things that were different, right? One of them being that we only access one line at a time when we're reading the data. We only access one line at a time when we're in direct mapping. When we do fully associative, all of these are available. That means every time I read it, I'm reading all of these. And when I write, I have the ability to write to any one of these lines rather than just saying, okay, I'm only going to write to a particular address, right? So that is a big difference between the two. And it means that I am going to take a little bit longer. It's a little bit more expensive to read it because I basically have access to all of this memory. And also for a fully associative, what you'll see now is these tags where it has 1 and 2. It's not just one block, one memory block, but it has multiple ones that you can go ahead and store the information in, right? Which means that you have a little bit more, you can store kind of like twice as much and you won't have as many clashes because you can instead of it just being a one-to-one, you can have more than one block stored in that um, same line of cache. And then here is this searching algorithm showing, okay, when I search, I'm looking at everything, right? Which makes it expensive to search. So let's see how that looks in terms of our program. And again, it's searching all these blocks in parallel. If I have the same program, when I look at my fully associative cache, I can store this first value here, right? And I is equal to 1. And then I have y, but notice how y now is stored in this set includes both of these here, right? Instead of me just having 1, I can have both of these addresses within this set because it's more than just one block and more than just a one-to-one, but I include both of these here. And let's go ahead and continue with that. Let's say now I want to store my Z. I can store that there, and I can store A there, depending on where I am. And also notice that I'm not doing this sequentially because I can access all of the sets at the same time, all of the blocks at the same time. It doesn't really matter where I write it. I don't have to do it in order. But you can just, pick whatever area you want to set the memory in. So that's also an important distinction as well. That I don't need to be tied to a particular memory location. Although this is going to be noted within the tags, it'll tell you the memory that is associated with the location. But this means that it's a set one, which will include these 2 blocks from your memory. This is set 3, which will include these 2 other blocks from the memory. All right, so, and then notice how this is just because I have access again for the fully associative, you have access to all of the blocks. So you can write to them and search them in parallel. Well, not write them in parallel, but you can search them in parallel, excuse me. All right. And last but not least, let's look at the set associative cache. Now, what you'll notice is that it looks similar. It's kind of like a marriage between the direct mapping and the fully associative. Not a marriage, like it kind of uses a little bit of both of the qualities. Where when you're searching one line at a time, right? You don't have access to all of them at the same time. You're not reading all of them at the same time. And you'll notice that if you're not reading them all at the same time, that's why you have these white spaces here. You only need to read one of these in each time. And another thing is that it's set associative, and for this, you would search it. You kind of search it in sequence, and you'll get where you have these blocks of memory here. And this again is going to have multiple blocks, right? Whereas our direct map had one block, one-to-one block. This one is going to give you multiple blocks that you can include from memory. And this top number refers to the sets, right? If we have a 4-way set cache, that means you have 4 sets that you can use within that particular set associative cache. So let's take, and when I say you search all entries in a set, this means that I'm searching everything here, right? If I'm at this one, I'm searching the information in this set all at once. So if I were to do this, if my set was, 4 blocks long, I'm searching all 4 of these blocks at once. Same thing here, I can search all of these at once, but I'm not searching the entire cache. I'm only searching the set that I'm interested in. So let's look at the data flow for a set associative cache. All right, let's start off out with x is equal to 1. What do I put that? I'm going to put that in the first set that I have here. And then if I have y is equal to 0, I'm going to go ahead and enter that into the second block, second location of my particular set. And you'll see, okay, this is going to go to that first place in memory. And again, you still have multiple blocks here. All right, we're mapping multiple blocks. And notice how now it's really going sequentially, right? So I'm going to go from this set, then I'm going to go to the next one. That's where I'm going to map it, and so on and so forth. It's really like a sequential right to this particular area, just because I'm not accessing all the sets at once. All right. So we saw something here where I have all this, but what happens? I now know how it kind of writes and stores the information in the cache, but what happens when my cache gets full? How do I know how I want to replace the information, and what am I using? What do I kick out? What do I keep? What happens when it gets full? Well, let's talk about that a little bit. There's a few strategies you can use to replace it. One is random strategy. And yeah, you've guessed it. That means that I'm randomly replacing the data in the cache. So we just whatever we want to replace, that's what we change it out with. And this is really easy to implement, but it has a small performance increase. And what that means is that the intent of the cache is to ensure that I can access the data that I use most recently rapidly. So if I randomly replace that, that means I may or may not uh, have access in the future to the one that I recently used. So the performance may not, you may not get as much of an increase as you want. So let's look at how that looks with our example. Let's, now this is, we're just using this as an example, but let's say we had this cache that was full with these numbers here, and this is kind of how we enter the data. At this point, x is equal to 2, right? I want to randomly replace the data. Now I'm getting down to this point where I have another extra variable, which is I. I'm setting equal to 0. My cache is full. Where do I put that? I got to put it somewhere. It's not currently in this set, so I need to determine where I want to put it. And a random replacement policy, I'll put it wherever, someplace randomly. So for this one, I put it in this set, or this is block 4, and that's where I'm keeping it. This should actually be I. Excuse me, I'm sorry about that, guys. So now I've a dot is equal to 0 is replaced with int I is equal to 0. So this is where it was previously, right? This is what that we had in there, and now we have replaced that with our new item indicating what I is equal to. All right. So that's a random replacement policy. Another one is called the least recently used, or LRU policy, replacement policy. And that means that whatever data that you haven't been using, you kick it out, just like spring cleaning, right? If you have all the stuff that you're not wearing or you're not using, get rid of it. So it says whatever data item I have not touched in a while, that's what I'm going to use. Now, this takes a little bit of thinking in terms of implementation, because you have to keep some sort of counter, or you have to keep track or know what you actually recently access and what you did not. But it has a pretty good performance increase, because if I haven't accessed that data in a while, likely I'm not going to be accessing it for a little bit. So that's similar to when we were looking at our for loop problem. It's similar to that, because now every time I increment X, I can basically, I won't replace that because I won't replace that immediately because I'm constantly accessing that. And then another thing about this is that the data stays in the cache. So rather than me randomly kicking out something that I'm using, I'm going to keep what I most commonly use within that cache. So let's look at an example of this. All right, so keep in mind when we think about what is most recently used, or the least recently used, we have these three numbers here, right? X, Y, Z, and A. And I need to figure out where I'm putting int I, right? Now, if I look at this, I would say, okay, X is really the one that was the first one I implemented. But at the end of this, I did actually update it, right? So it was just recently updated to 2, right? So I'm not actually going to replace that one. What we're actually going to do is we're going to replace Y because that was not recently used. That was not recently accessed. So because of that, that will be the one that's chosen to be replaced in the cache, right? So hopefully that makes sense. Rather than us randomly choosing it, we say Y, which was my first second variable that was set, but my one that has not been used recently, that is the one that we're going to use to replace in this particular action. And then this becomes our new cache set. And finally, FIFO, FIFO. We hear this often, right? First in, first out. And what we do is we replace the data that has been in the cache the longest. That is what is replaced first. And it doesn't necessarily mean that it's the most recently least used, but it just means that whatever was in there the longest, that's what we're going to replace. It's relatively easy to implement, and it has a moderate performance increase, but it does require a counter because you need to determine what was actually put in there first, second, third, etc., in order to know what you're going to kick out. And here's what it looks like. Sorry. Here's what it looks like from our data, from our perspective. If I start out with our original thing, what am I going to replace? I'm going to go ahead and replace x is equal to 2 because that was the one recently left out of the cache. So now let's look at the data requests and how that flows. We know that we start out in the processor. You say, hey, I want to do something. Let's say I want to retrieve my value for x. Processor, tell me, what is x equal to? It's going to request the data. And what it's actually going to look at first is the cache. That means, okay, can I easily access this information from my cache? A hit means yes, I was able to retrieve it. I can go ahead and feed that information back to the processor. And then the processor tells you X is equal to 23, right? That's a hit. That's all good. That's a successful data retrieval. But the other option is I miss it, or it didn't find the data in the cache. And in that case, it will go ahead and look for it in memory. Now, of course, each time you miss it, you're taking a little bit more time because now you searched in 2 places, right? So each time it misses it, it's going to go ahead and search the memory for it, and that's what we call a miss. Now, what we want to do generally when we do this cache information is we want to avoid misses. We don't want to keep on missing the data because it means that we're taking longer and longer to access and get the information. So you'll hear some people talk about, the miss rate and the hit rate. And we'll talk about that right now. So a miss rate can be calculated in 2 ways, or you can think of 2 ways to do it, right? The number of cache misses. Now, keep in mind that a miss means that I was not able to access the data from the cache. It's not there. It doesn't, it's not within the cache, and I have to go down and go to memory, divided by the number of requests, right? So let's say I have 10 lines of code where I'm saying what is X, Y, and Z, A, B, and C, D, E, F, and Q, right? I want to know what the data is for all 10 of those. And let's go ahead. Let's write this out as an example. Similar to my for loop, let's say I want to access X, Y, Z, A, B, C, D, E. Okay, I'm gonna have to go up here. That is 5, 8. And we'll make this P and Q. All right, so this is a total number of 10, right? And now let's say in my cash, my cash, I have X is 3, Y is 5. A is 15. Q is 4. Um, Q is 4. I'm gonna have B is equal to -5. And we'll set up C equal to 15. All right, let's say this is what I have currently in my cash. And let's look at this one, right? My number of requests is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So what the heck? Oh, this is Q. So let's look at kind of our hit and miss here. This is Q. So we go to Q. Can we find that? Yes. So we're going to write that as a hit. The next one is P. Can we find that? No. So this is a miss. X, find that, hit. Y, we find that, hit. Z, I'm guessing that's what that is. Not there, that's a miss. A, hit. B, miss. C, which is 15, that's a hit. D is a hit. And E is a miss. All right, so from this, looks like my number of cash misses are 1, 2, 3, 4. So my miss ratio for this would be 4 to 10, or, as you do a little bit of conversion and math, you end up with 2/5. That's your miss ratio, approximately 40%. Now, one of the other things is, right, we talked about what misses are and what hits are. Hits are anytime you find the data. So another way I could have done that is if I wanted to determine a miss ratio, I could also use this formula here. 1 minus the hit ratio. So that's 1 minus the number of hits, the hit ratio that I have. So let's talk about what hit ratio is. Hit ratio is going to be a little bit more involved. It's going to be the number of cash hits divided by the number of cash hits plus the number of cash misses, right? So it's not necessarily the total number of requests, but the number of hits and misses. That's going to be your hit ratio. And another way you can calculate that is basically 1 minus your miss ratio. All right, so we talked about the more hits you get, the better. uh, because if you have a high hit rate within your cache, it means that you're accessing the data more quickly and you don't have to go with memory as often. So we always try to balance the type of mapping and uh, data replacement with the ability to have few hits. But we balance that between the hits and also the complexity with implementing that particular uh, association in that particular memory type. So let's look at how these cache mapping types kind of match up. When we look at direct mapping is going to have a high miss rate, right? And why is that? That's because, like we said before, there's this one-to-one relationship. So every time I get full with the memory, then with the cache, I'm going to have to then replace it or figure out how to access the information. There's also some other things that make this direct mapping have look at a high miss rate. Now, the other thing is it's really easy to implement and you can quickly access the data because if you remember from before, the tag or that information, the block is going to be have a one-to-one relationship with where it is in memory. So if I say, hey, I want to access this memory right here, I don't have to go through each set. I know where it is because there's a one-to-one relationship between that and where it's located in memory. And I can also, because I know where it is, I can access the data quickly. And I have a low read resource usage because I know where the data is. Now for fully associative again is where you can access all of the sets all of the time. Um, and you can also you can map multiple blocks in one line. And what you'll notice is that it's a lower memory and lower miss rate because I can store information. And I'm not as stringent in terms of the one-to-one relationship between memory and the blocks in the cache. It's relatively easy to implement. Um, but the disadvantage of this type is that it has a high resource usage. And that's because I'm reading all of these in parallel. So I'm using a lot of my CPU time and effort to read all of these at the same time. And finally, we're talking about the set associative uh, cache mapping. And this has a low miss rate, lower than the other two mapping types. And it's a little bit difficult to implement because you're looking through and searching through those particular sets. You have to figure out what set your memory item is. You're doing it one by one. That's also why the data access is moderate because remember when we search this set, as you remember for the other ones, we're doing this sequentially. So we have to, determine how to get that data in sequence, and we're also the read usage is it's moderate to low because we're looking at two sets at once as opposed to so remember for the set associative, you're looking at how many of our sets are within, how many of our blocks are within your set. So you're still accessing multiple things at once, as opposed to just doing one block at a time. And this is kind of a table that can kind of we can keep in mind as we look at which mapping scheme we prefer to implement for the cache, right? Direct mapping, super easy to implement, low cost, low complexity, quick data access, but your miss rate is going to be high. Fully associative, it's moderate, it's low complexity. You have quick data, um, but you may still get some misses there. And instead associative, it's going to have the one of the lowest miss rates you'll get for out of these, and it also the data accesses is so-so. It's kind of between the two. It's a little bit more complicated when we think of how we're going to implement it, and the cost is also moderate. So that kind of gives a summary of what we're looking at for cash. The next lecture or the things that I will post will be kind of these examples of how we use that and how we implement that and do some calculations associated with this. All right. Thank you all for joining me for this lecture, and I hope that you enjoy the rest of your day.